Hi class, welcome back to the next acid-base lecture for chapter 14 in the OpenStax book. And in this lesson we're going to cover what is summarized in section 14.2 regarding pH and pOH, and we're going to relate that to Kw, which we discussed in the previous lecture. So let's go ahead and get started with this. We're first going to take a look at understanding the acidity of solutions. So the acidity of a solution is going to be directly correlated to the amount or the concentration of the hydronium ion or H+. So we use those interchangeably. Hydronium is going to be if you have H+ present in water, and then if you are outside of water, let's say you are in some sort of an alcohol solution or something else, then sometimes you may just refer to it as H+. Okay? So it's the concentration of the H+ or the hydronium that is important. Now, this can be examined when we're looking at the molarity, and we're going to relate this in the next lecture to equilibrium constants. So we've been working with equilibrium constants. We know that concentrations are important in calculating Kcs. So instead of Kc, there is something called Ka, and we are going to start calculating the equilibrium constant specifically for an acid. And the concentration of H+ is really going to be how we determine how acidic it is. Okay, now we can simplify the concentration numbers if we want to talk about it in more simplistic use, in sort of everyday use, to a logarithmic transformation. Specifically, we're going to take the negative logarithmic transformation of the acid concentration. And that gives us what everybody is usually familiar with, which is pH. So this little p is placed in front of things when they undergo a negative logarithmic transformation. And that P can be applied to many things. So I just mentioned Ka, you can have pKa, right? But pH is probably the best known out of the bunch. Right? So by taking the negative logarithm function of the acid concentration, we'll obtain the value of pH. And it is important to understand that because we're taking a negative logarithmic transformation, this is going to set up an inverse relationship to the concentration. So what that means is, as the concentration of acid goes up, the pH comes down, right? So if you think back to general chemistry, Chem 111, anything you may have taken in high school, we learn generally that the pH scale is set up from 1 to 14, with 1 being essentially the very acidic acids, and then we continue to climb. 7 is around the neutral point, and then it goes all the way up to 14. So if 1 is the most acidic, that means that the concentration of hydrogen ions should be very high in a superacidic solution, but the pH is going to be very low. So just keep that inverse property in your mind as we're dealing with this. All right, so what happens if we have the pH and we want to go back to the concentration? Because we want to be able to readily convert back and forth. If somebody gives you a solution and they say this acetic acid solution has a pH of 4.5, you want to know how much H+ concentration is in that acetic acid solution. So you want to be able to take the pH and backpedal. Okay, so since the concentrations are originally transformed on this negative logarithmic scale, you can basically undo it by using the antilog, and the antilog for the log scale is 10 to the minus, and then you put the value there. So the value in this case would be the pH, and if we take 10 to the negative pH, that will return the H+ concentration that would be present in the solution. Right? So what I'm going to do is just go through 1 or 2 examples that you can find in the OpenStax textbook. This should be very easy to follow along with, so just have a calculator out as we go through this briefly. Okay, so we're going to set up a pH calculation really quick, as well as a reverse where we take the pH and convert it back into the hydrogen ion concentration. Right, so there is a problem in the book that refers to stomach acid, which is HCl, and it says that it has an H plus concentration that is equal to 1.2 times 10 to the negative third molarity. So the question is, what is the pH of the stomach acid? So in order to do that, all we would have to do is set pH equal to the negative log of 1.2 times 10 to the minus third. And what we end up with, if you put that into your calculator, is 2.92. Now I want to take a moment here to point something out, because a lot of students can get confused with this, particularly the significant figures. So up here, we can see that we have two significant figures. And down here, it would appear that we have three significant figures. However, that's not the case. And this is something that occurs, it's special to these logarithmic transformations, because what's happening is that this 10 placeholder is getting wrapped up in the negative logarithmic term when it gets transformed. And this is normally not considered for sig figs. So this first value here that comes out is a result of that placeholder. And when we have this, we want to ignore it. And the correct way of reporting this is you want to take the number of significant figures in the concentration and go that many decimal places past your pH level. So in this case, we had two significant figures that were present in the H+. So therefore, I go 2 decimal places out past the 2, which is a placeholder for the general amount that we're dealing with here. Okay, so I just wanted to be clear with that so that people weren't confused when they look at the examples in the book or they're going on and watching videos to practice and they say, why do I keep seeing 2 significant figures and then 3 reported back, or 3 significant figures and 4 reported back, so on and so forth. Okay, now, in the same vein, let's talk about doing a conversion backwards. So now, let's say that we have a pH, and you're given a pH and it says the pH is 7.3. Well, in this case, we want to convert, and we would have to take 10 to the negative 7.3. And if we do that, that will equal the concentration. So this will become the H plus concentration. This is going to equal 10 to the negative 7.3. This is the anti-log. And then when we put that into the calculator, you should get 5 times 10 to the negative 8th. Okay, now 1 here, because remember I'm working in reverse. So placeholder, 1 significant figure, because there's only 1 decimal place. So therefore, I'm only going to look for 1 sig fig when I come back here. All right, now we will practice these in class, so you'll get used to this going back and forth with the conversions. But I did want to bring up this work here so that we could not only look at how we calculate these in the calculator, but also discuss the significant figures, because they're going to be important there. Okay, so as I mentioned earlier, this is not the only type of logarithmic transformation that we can do in relation to the hydronium ion. So there are lots of other forms, and some of those are pOH. So there is such a thing as pOH. That's simply the P of the hydroxide content. There is pKW. So we already discussed KW. KW at 25 degrees Celsius would be 1 times 10 to the negative 14th. So we can take the pKW, and then, as I mentioned earlier, there are pKa's, which are representative of the equilibrium concentration setup for these acids. And pKa's are really going to help us create a scale where we can determine if something is a weak acid or a strong acid. It gives us a little more variability than the pH scale. The pH scale is fairly general in comparison to the pKa scale. And as we progress through the next couple of lectures, you'll understand what we're talking about here. So we can relate pH and pOH back to pKw, because remember, in the first lecture, we talked about that Kw would be equal to the concentration of the H plus times the concentration of the hydroxide, right? And then water would be removed. As it's a liquid, it's not going to play into an equilibrium constant. Okay, now this is very important because what if you only can measure the hydroxide content of a solution, but you want to know its pH? Well, by finding the pOH, you'll be able to find the pH. So some useful equations here that are highlighted outside of just the pH is Kw, again, is equal to the concentration of H3O plus and times the hydroxide concentration. And then pKw is going to be equal to pH plus pOH. Now, when we convert Kw into pKw, and you can try this out in your calculator, we're going to take 1 times 10 to the negative 14, and that is going to become 14. And this is where we get the cap out level for the pH scale at 14, because we say that the H plus and the OH combined together makes Kw. Well, Kw has that 1 times 10 to the negative 14th value, so when we transform it, we get 14, and so the cap on the pH scale is going to be 14. And it will always be 14, and it's a combination of the pH and the pOH that have to add up to that. Okay. So we're sort of discussing and going back and forth with these values, but where do we actually determine the cutoff if I want to say something is an acid or a base? And a lot of students already know this because this is usually high school chemistry, but I want to discuss something important here. All right? So in general, the concept of an acid is going to be anything below a pH of 7. Anything that is exactly at a pH of 7 will be considered neutral, and that's our typical thought of water. Now, almost all water is not exactly at a pH of 7. It might be slightly above or below, depending on the different ions and other materials that are in the water. And then we can also talk about basic solutions, and those are going to be any that have a pH that is greater than 7. Right? Now, what's very important here is that these cutoffs, when we talk about the 7 mark being the neutral point, and then we tip either down low to an acid or up high to a base, that's based on Kw being at 14, and Kw or pKw is only at 14 when it's at 25 degrees Celsius. So the value that we give you for Kw, that's an equilibrium constant, and equilibrium constants are subject to temperature, which we've discussed in great length in the last chapter. And because of that, the pH ranking or break apart here that we have listed is valid at 25 degrees Celsius. Right? And you can even see on the table, pulled right from your book, it says pH at 25 degrees Celsius. So this means if we increase or decrease the temperature, we're going to screw around with the Kw. And if we screw around with the Kw, or the pKw, then that means we would also be screwing around with what makes technically a neutral pH or pOH cutoff, because they are built into the Kw equation. So just keep that in mind. If you want more information, you are welcome to go over to your book, which I just brought up here, and you can see that they do have some examples in here where they talk about the difference with the temperature. So I would encourage you to go through here. I'm actually trying to look at where that specific example is. Here it is, right here. Okay, so it says, it's talking about the Kw, and it says the pH negative log H3O plus, and it's 6.31 is the variability point, okay, at 80 degrees Celsius. So this is an example where they say, what if we had water at 80 degrees Celsius? Okay, and then they talk about the different values associated there versus at 25 degrees Celsius. So just keep in mind, in our class, we're almost always going to be operating under the assumption we're at 25 degrees Celsius. We do that for the thermodynamic data. We've done that for a lot of the equilibrium material. So it's usually a safe bet, but just be aware that this can change. Okay, and then I just brought up this chart here. Again, you can find this in your book. It gives some of the relative variance in acidity for common things that you might come across. So we have 1 molarity HCl, That's very acidic on the scale, a pH of 0. And look, you can even get to a pH that's negative if you get concentrated enough. All right, then we have gastric juice. So our stomach acid is pretty intense, and that's by design. We have to have very strong acid in order to break down the biochemistry involved in our food, which includes proteins, carbohydrates, and fats. Okay, we got lime, lemons, things of that nature. Vinegar, we're starting to get a little bit weaker. Then we have the things that we would drink on a regular basis. Most people don't drink lemon juice or lime juice. They add it for flavor. But we start looking at wine, orange juice, coffee. So those are things that are acidic, but not so acidic that we can't handle them or drink them compared to something like concentrated acid. You have rainwater. Pure water is at our neutral point. That's at 7, again, assuming 25 degrees Celsius. Blood, keep in mind that blood, when it's on this chart here, is extremely tightly regulated. The pH of your blood is not able to go very far out of the buffer range that is set up. Okay, and then you can continue to look here. Ocean water, baking soda, milk of magnesia, and now we're starting to get into very basic compounds. Household ammonia, a lot of your cleaners, bleach, and then finally we get to some chemical grade 1 molar sodium hydroxide. Right, you could put some other things in here, such as Drano, uses some level of sodium hydroxide to clear your drains out. So that's a general overview of the scale here that we would look at. Okay, so that wraps this one up. Up next, we're going to be taking a look at acid-base equilibrium, which is really directly related to acid strength. So when I was talking about Ka, pKa, all of that sort of stuff, we're going to start to look at some of that. So until next time, thank you very much for your attention, and I will see everybody over in the next lecture.